Hello, my dear students. The topic of discussion in this lecture are fundamental theorem of linear programming problem, and then we will describe how can we reduce a feasible solution to a basic feasible solution. On the last lecture, I was describing the equivalence between a basic feasible solution and an extreme point of the feasible set. We have found on the last lecture that any basic feasible solution to an LPP corresponds to an extreme point of the feasible set, and then also we have proved the reverse result. Any extreme point of the feasible set is a BFS. We have proved on the last day. Today, with the help of the results collectively that we have described so far, if we recollect, we will find that we have described at first that if there exists an optimum solution to a linear programming problem, then the optimum solution must coincide with one of the vertices. Then we have proved any vertex is a basic feasible solution. And therefore, if we just club these two results, then we'll find that if there exists an optimum solution of a linear programming problem, then the optimum solution must be coincident with at least one of the basic feasible solutions. Fine, and that is the fundamental theorem of linear programming problem, which states that if there exists an optimum solution of a linear programming problem, then the solution must be obtained at least one of the basic feasible solution of the feasible set. Fine, that is just um, amalgamation of two results, those we have described so far. So I'll just state that result, and then we notice the following, that once we state the fundamental theorem of linear programming problem, that if LPP admits an optimum solution, then the optimal solution must coincide with at least one of the basic feasible solution of the feasible set. Here is a question before us, that given that LPP admits an optimum solution, where is the guarantee that the feasible set will have a basic feasible solution? And therefore, in this lecture itself, we will be trying to prove that if there is a feasible solution to an LPP, then there must exist at least one basic feasible solution of the feasible set. Fine. So in this lecture, we'll describe then how do we reduce a feasible solution to a basic feasible solution. Then we'll execute a problem so that the idea will be very neat before us. Let's start stating the result, the fundamental theorem of linear programming problem. Which states the following, that if there exists if an LPP admits an optimal solution, that means there exists a finite optimum of the objective function of the given LPP in the given constraint set. If an LPP admits an optimal solution, then the optimal solution must coincide, then the optimal solution must coincide with at least one BFS of the feasible set. Fine. As I said, here is a question that LPP has an optimal solution. So there exists a solution, or there exists a feasible point of the given LPP. There exists a feasible point means there exists at least one x such that ax equals to b and x greater than equals to 0. Fine. Now given a point for which you have x equals to b together with x greater than equal to 0, how can we confirm that this set x equals to b greater than equals to 0 has a basic feasible solution? The assurance is to be proved later in the following result, which is the reduction of a feasible solution to a basic feasible solution. Reduction of a feasible solution to a basic feasible solution. So we start letting a feasible solution is given before us, then we will reduce it to a basic feasible solution, and inside the proof the process will be known to us. I state the result as a theorem. If there exists a feasible solution by a feasible solution or a feasible point, we mean the same, that there exists a point x such that ax equals to b together with x greater than equals to 0. By feasible solution, we mean a feasible point or just a point x which satisfies ax equals to b together with x greater than equals to 0. If there exists a feasible solution to this set, then there exists a basic feasible solution to the set S. Fine. Now let me prove the result. The proof will be as follows. So let the given point, which is a feasible point to the set S, is, let's suppose it is x star. So let x star be a feasible point. X star be a feasible point. Here you notice that then in x star you may have a few components 0, a few other components those are non-zero. So either 0 or non-zero components of the x star will be fine. So interchanging the roles of the variables just by rearranging or renaming the variables, we can without loss of generality write the solution x star as, at first let us write the non-zero components x1 x2, then so on xp, then rest of them are all zeros. Fine. Here are n many components. Here you have n minus p many components, and here you have all these are non-zero, x1 x2 xp's all are non-zero. Once these are all non-zero, then obviously they will be greater than 0 because x star is a feasible point to the set S. So x star should satisfy greater than equals to 0. Once these are non-zero, therefore they will be all greater than 0. x1 greater than 0, x2 greater than 0, and xp greater than 0. Instead of writing x star, let me write with x bar, so that the writing will be little bit clean. X1 bar, x2 bar, xp bar. Fine. So let x bar be a feasible solution feasible point of S. Fine. And here we must write without loss of generality. Without loss of generality, which we in shorthand usually write WLOG, without loss of generality. And here, how we are not losing the generality? That we are writing first few components non-zero, and then later on the components are zero. Here you may have this p. P is in between. P can be all zeros. All the components may be zero. In that case, p will be just zero, or at max it will be n. Fine. So without loss of generality, we are keeping the first few variables of x bar non-zero. Then later on, all the components are zero. Fine. Here we are not losing any generality on taking the point x bar, which is a feasible point, because here interchanging, if required, then we interchange uh, the roles of the variable. So here we, if required, then we rearrange the rearranging if required. Rearranging the variables if required. The variables if required. Fine. Now we'll reduce this x bar to a basic feasible solution. Fine. Now, if your p is equal to 0, if p is equal to 0, then we notice that um, we have two possibilities, that the set, then either the set S consists of only 0, or else, or if S is not equals to 0, then either this, or we consider a point or S is not equals to 0. So S contains a non-zero point then. Or we consider a point of S and name it as X bar. At X bar. Then again you start. So without loss of generality, then we can assume P is greater than equals to 1, right? So at least one component there is at X bar. If S equals to 0, in that case, if P is equal to 0 and then you also have S is equals to 0, then so you have two possibilities here. If P equals to 0, then either S is equals to the singleton set 0, or otherwise S is not the singleton set 0. In that case, in capital S, you will have a non-zero point, and then you start working with letting that non-zero point as X bar, then you proceed with the proofs. Or else, the leftover case is if P equal to 0 together with S equals to the singleton set 0. Then in that case, the set is just the point origin. And if the set S has the point only origin, then that is indeed an extreme point, right? And that is obviously a basic feasible solution, because just a singleton point is having only one, and that point is the extreme point, and obviously that is a basic feasible solution. So now so without loss of generality, next we assume that p is greater than equals to 1, and we are letting that then x1 at least is not 0. So without loss of generality, so here if s equals to 0, then the point 0, by this s equals to 0 means this 0 is the vector 0 in Rn. Fine. Then this point 0 is an extreme point, and therefore it is a basic feasible solution to S. And the proof is over, because in that case the optimum solution will be 0. Trivial. Fine. Therefore, without loss of generality, we are assuming that p greater than equals to 1. Therefore, without loss of generality, we assume that p is greater than equals to 1. Fine. Now we consider the vectors. Here p greater than equal to 1, so p can be 1, p can be 2, at least one p is. Fine. P can be 2, p can be 3, whatsoever, but p is less than equals to n. Fine. Now here the point x bar is given to us. This point is a feasible solution, it is also given to us. Now we'll check whether the point x bar itself is a basic feasible solution. If it is a basic feasible solution, then the proof is done that there is a basic feasible solution. If x bar is not x bar is not a basic feasible solution, then we have to proceed with how can we reduce this feasible solution to a basic feasible solution. Now, under which condition x bar will become a basic feasible solution? This point x bar is a basic feasible solution provided the vectors, the column vectors in the matrix capital A associated to the variables x1 bar, x2 bar, xp bar. That means the vectors a1, the first column vector of capital A, a2, the second column, ap, these p vectors a1, a2, ap is linearly independent. If linearly independent, then obviously the point x bar is a basic feasible solution. And if not linearly independent, that is linearly dependent, in that case it is not a basic feasible solution. Then how can we reduce this feasible solution to a basic feasible solution? That we have to endeavor. Fine. So let me now start with writing that if the column vectors a1, a2, AP, those are column vectors associated to the variables first p. That means first the non-zero variables. These vectors, these a1, a2, AP are the column vectors of capital A, which are associated to the non-zero variables x bar. If this set, the set of column vectors of A is linearly independent, then the point x bar is a basic feasible solution. You might ask the following question: what is the matrix capital B associated to the vector x bar, because corresponding to any basic feasible solution, you all know that corresponding to any basic feasible solution xb, what we have, a matrix B of order m by m, which is a non-singular submatrix of the matrix A, such that you have bxb is equal to small b. This is how we construct a basic feasible solution, right? How do we get a basic feasible solution? Is that from the given matrix capital A, you choose one m by m non-singular submatrix capital B, and then you consider to solve this equation bxb equals to b, and you get a basic feasible solution. And therefore, corresponding to every basic feasible solution, you have one m by n submatrix capital B of the matrix A, such that bxb is equal to b, and vice versa. Vice versa means corresponding to any non-singular submatrix capital B of the matrix A, there is a basic solution. Fine. Now, corresponding to this x bar, a basic feasible solution, here you note that the feasibility we don't have to check. By feasibility, we mean the non-negativity restriction of this x bar has not to be checked, because x bar you have already taken here all the components are greater than equals to 0, because it is a feasible solution. So feasible solution x bar it is. So we have to just check whether this is a basic solution or not. Then x bar will become a basic feasible solution. So here, to prove that it is a basic solution, x bar is a basic solution, what do we have to prove? We have to prove that there exists one m by n non-singular submatrix of the matrix capital A, by which you will obtain bx equals to b and xb will be equal to the point x bar. Fine. We just have to show there exists one m by m submatrix which is non-singular, and this submatrix is a submatrix of the matrix capital A. And how do we construct it? The construction is the following. That construction is already given on the last day's proof, when we are proving that any extreme point is a basic feasible solution. Let me repeat once again. Here you notice that A1, A2, AP is linearly independent here. Then we are claiming that it is a basic feasible solution. If linearly independent, A1, A2, AP, and here A1, A2, AP, all these column vectors are m-dimensional, because any column vector AI of the matrix capital A, AI is belonging to Rm, right? And therefore, a set A1, A2, AP in a set of linearly independent vectors, you can have at max m number of vectors. Fine. So a set of linearly independent vectors from Rm can have at max m number of elements. Fine. That we know. And therefore P is less than equals to m. If P is equal to m, then you consider this matrix capital B as A1 as the first column, then A2 as the second column, AP as the pth column. Fine. And then you notice that the determinant of the matrix capital B is non-zero, and therefore B is a non-singular submatrix of capital A, and it is of order m by m. And that will prove that x bar is a basic solution, no doubt at all. Now, if P is strictly less than m, if P is equal to m, then you construct this capital B. Now, if P is strictly less than m, then what we have to do? We notice that then A1, A2, AP is no longer a square submatrix, no longer m by m. Then what we do is the following, that out of the other columns of the matrix capital A, other columns means you have, what are the other columns in the matrix A which are not in B? You have AP plus 1, AP plus 2, and then an. Out of these n minus p vectors, you keep on inserting on the matrix capital B, you keep on inserting minus p many elements. You keep on taking minus p many elements from this n minus p many column vectors such that those n minus p many chosen column vectors out of this n minus p many column vectors of A together with this A1, A2, AP will be an Li set, will be a linearly independent set. So what am I saying is the following. Here, if P is still less than M, then the order of the matrix capital B is obviously P by M. Fine. You have no M by P. Sorry, you have M many rows. M by P is the order. But in order to make it is M by M, then what we do is we insert a vector. So at first you choose the vector AP plus 1 and check whether AP plus 1, if you insert in this set A1, A2, AP, whether that set A1, A2, AP, then AP plus 1 is linearly independent. If linearly independent, then you check whether P plus 1 is equal to M. If P plus 1 equals to M, then that will be your set capital B. Fine. If if A1, A2, AP plus 1 is linearly dependent, then you drop taking AP plus 1 inside the set, inside this set, and then you choose AP plus 2 and then check whether A1, A2, AP and AP plus 2 is linearly independent or not. Fine. If linearly independent, then you proceed taking another vector AP plus 3 and then again you check whether A1, A2, AP, then AP plus 2, then AP plus 3 is linearly independent or not. If linearly independent, then you check whether the order of capital B is M by M or not. If not M by M, then you insert one more variable, one more vector out of these n minus p vectors inside the set. So in this way, you keep on taking vectors from these n minus p many vectors, keep on taking, and when you are taking off, you have to confirm that once you have taken AP plus 1 inside the set, this A1, A2, AP, then you check at first whether AP plus 1 is linearly independent with A1, A2, AP or not. If not linearly independent, then you don't insert it. Go for the next element. In this way, what you can do is you can construct a matrix B bar together with A1, A2, AP. Then you may have AP plus 3, you may have not AP plus 4 but AP plus 7 say, and so on. Fine. An. So that matrix is becoming M by M. Fine. And in this way you have a vector B bar, you have a matrix B bar, and with this B bar now you consider the basic variables. What are the basic variables? The basic variables are your x1, x2, xp, xp plus 3, xp plus 7 and xn. And you notice that the xp plus 3, xp plus 7 and xn, if you put them equal to 0, then b bar x is equal to b will reduce to b into x bar is equal to b, right? And therefore if x is a solution of this b bar b, then you have b into x bar is equal to b. Fine. And that will prove that the point x bar is a basic solution. Fine. Although it is a degenerate basic solution. Fine. So that in the case of when this when this p is less than m, we can still observe that the point x bar is a basic solution. Fine. So this is the case when a1, a2, ap is linearly independent. If linearly dependent, then obviously x bar is not a basic solution. So in that case, how do we reduce the point x bar to a basic feasible solution? It will be as follows. If A1, A2, AP is linearly dependent, then then obviously the point x bar is not a basic solution. Then let us go further and try to find out a basic feasible solution from the point x bar. If this is linearly dependent, then obviously by the definition of linear dependence of a set of vectors, then there exist scalars lambda 1, lambda 2, lambda p, not all zeros. So here we let lambda r is not equal to 0, such that you have lambda 1 a1 plus lambda 2 a2 plus till lambda p ap is equal to 0. The definition of linear dependence. Fine. So from here, so we name it as, let's suppose, 1, and now as x bar is a feasible solution to s, you have x1 bar a1 plus x2 bar a2 plus xp bar ap, then plus rest of the components are all 0, equal to b. I have written here in this equation, this is nothing but x bar is equal to small b. Fine. These we are naming as 2. Now from 1, as lambda r is not equal to 0, then we can write the vector ar as linear combination of the rest of the vectors. How? It will be as follows. We divide on both the sides by lambda r. As lambda not equal to 0, you can divide by lambda r. And then you keep ar on the left hand side and send all the other components on the right hand side. And accordingly, you will obtain it is minus of lambda 1 by lambda r into a1 and then a2 and so on, all of them. So I am just considering I here, and it will be summation from I is equal to 1 to p, but I is not equal to r. Fine. This is your ar, which together with b together with 2 produces the following, that I just now instead of AR here, I am just considering to write AR in terms of rest of the AIs. So in the equation number 2, so I will be getting the first as x1 bar a1, the second element is x2 bar a2, then r minus 1th element is xr minus 1 ar minus 1, then xr bar into AR. AR I am replacing by this. So minus I is equal to 1 to P, I not equal to R, lambda I divided by lambda R, AI plus XR plus 1 bar, AR plus 1 plus so on, XP bar AP is equal to B. Okay, now this will give you the following. Now let me collect the coefficients of all the vectors a1, a2, ar minus 1, ar plus 1 till ap, and then what will you get is the following, that the first component, that means the coefficient of a1 is x1 bar minus, here also you have one a1 inside of this bracket, and that a1 is lambda 1 by lambda r into xr together with a negative sign. So negative sign of x r bar divided by lambda r into xr bar into lambda I. Fine, this lambda I here is also I, then into ai. This summation in the summational form I'm writing it. It will be I equals to 1 to p I not equals to r is equal to 0. Fine. And then here you notice that, so therefore you notice that I am now constructing x star as the first component is x1 minus xr bar by lambda r into lambda 1. Second component as x2 bar minus xr bar divided by lambda r into lambda 2, and so on. Similarly, the r minus 1th component is xr minus 1 minus xr bar divided by lambda r into lambda r minus 1. Then the component is 0 because lambda r, that ar is not there in this equation, so the rth component is 0. Then you take off xr plus 1 bar minus xr bar divided by lambda bar into lambda r plus 1 and so on. Then the last component is your the pth component, that is xp bar minus xr bar divided by lambda r into lambda p, then rest of the components as they were in x bar. Fine, these are your n minus p many. Fine, so I'm taking off, I'm now constructing this x bar, and this x bar is indeed a feasible solution of the set S, because of, okay, not sorry, not feasible solution, but it is satisfying, uh, is a feasible solution to ax equal to b because of this equation, because of 3, because of 3. Fine, so because of 3 we notice that this x star is satisfying ax star is equal to b. Fine, now in order to make that x star a feasible solution, what we have to make, we have to make all the components here, all of this xi bar minus xr bar divided by lambda r into lambda I is greater than equals to 0 for all I from 1 to p. Fine, and I not equal to r. So how do we make it? For that, let me now make a note here. Notice that x star is a feasible solution to ax equals to b together with x greater than equals to 0, if you have xi bar minus xi bar minus xr bar divided by lambda r divided by lambda r into lambda I greater than equals to 0 for all I equals to 1, 2 till r minus 1, r plus 1 and p. And now we analyze that when this all will be greater than equals to 0. That is, if you have, you notice that here this lambda I can be 0, can be non-zero. If it is 0, then obviously xi bar is greater than 0, so this component is greater than equals to 0. Fine. So if, so you don't have to take any restriction if lambda I is greater than 0. If lambda I is equal to 0, no restriction is required. So you just take as it is, and if lambda I is not 0, so it can be either greater than 0 or less than 0. Then if it is greater than 0, then what you require to have is, if lambda I is greater than 0, then you divide on both the sides by lambda I. So you will have xi divided by lambda I is greater than equal to xr bar divided by lambda r. Fine. And if lambda I is less than 0, then we notice the following. Then you will require, if lambda I less than 0, then this inequality, if I divide by lambda I, then this inequality will be getting reversed, and accordingly you will require to have xi by lambda I less than equals to xr bar divided by lambda r. Fine. So what restriction do you require? What restriction do you require such that all these components are greater than 0? And how can we make all these components greater than 0? And where is your liberty of choosing something such that this will be greater than equals to 0? The choice in which you have a liberty is the choice of this variable r. Because here notice that you have chosen one r such that lambda r is not equal to 0. You have chosen one r such that lambda r is not equal to 0. Fine. And you can vary this lambda r. If you, here you notice that if there exists only one lambda r which is not 0, and rest of them are all 0, that will not be possible, because lambda, let's suppose all the components are not 0 here, lambda 1, lambda 2, all of them are 0, sorry, lambda except lambda r, let's suppose all lambda I is 0, then this equation will be leaving over you that lambda r into ar is equal to 0. If ar is a non-null vector, then obviously lambda r into ar equal to 0 will imply lambda r is equals to 0. So just one lambda r is not 0, not possible. Fine. And therefore there must exist at least one another lambda I which is not 0. Fine. And therefore you have a liberty of choosing r out of at least two possible indices out of 1 to till p. Fine. And so here is a choice that you choose one r such that these two restrictions are valid. These two restrictions you are requiring. So this for lambda I greater than, if lambda I is equal to 0, you don't require any restriction, because if lambda I is equal to 0 for some particular I, then in that case you will observe that this is automatically greater than equals to 0. So you require to choose R such that these two inequalities are happening. By these two inequalities are happening, we now try to collect out what is the essential condition. The condition here that you choose R such that for lambda I is greater than 0, that means you find out those i's for which lambda I greater than 0, then you consider to find the position of xi bar divided by lambda I real number line. Here is your real number line, here is the location of 0, say. As xi bars are all 0, all greater than 0, therefore if lambda I is greater than 0, therefore xi bar by lambda I is greater than 0, and if lambda I is less than 0, then xi bar divided by lambda I is less than 0. So let's suppose lambda 1 is greater than 0, and here is the location of, let's suppose, x1 bar by lambda 1. Let's suppose lambda 2 is also greater than 0, and here is the location of x2 bar divided by lambda 2. Let's suppose lambda 3 is less than 0, then here will be the location of x3 bar divided by lambda 3. Let's suppose lambda 4 is greater than 0, and here is the location of x4 bar divided by lambda 4. Let's suppose lambda 5 is negative, and here is the location of x5 bar divided by lambda 5. So in this way, we are now locating all the values xi bar divided by lambda I. So these are all locations. These are all positions of xi bar divided by lambda I. And now you have to choose R in such a way that xi bar divided by lambda I. Sorry, x bar R divided by lambda R is less than equals to xi bar divided by lambda I for all I such that lambda I greater than 0. Fine. You have to be smaller than all the positive quantities. So you can choose this is your x r bar divided by lambda r. And here this restriction is saying that x r bar divided by lambda r has to be bigger than all the negative quantities. Fine. So you choose x r bar by lambda as either this quantity or this quantity. Then we are noticing that x r bar divided by lambda r is smaller than all the positive quantities, and it is also bigger than all the negative quantities, right? So you choose either of either this or this, then it will satisfy both the conditions. Now here you notice that lambda r is either positive or lambda r is negative. If lambda r is positive, then in that case you have to choose this, and if lambda r is negative, then you have to choose this. Fine. So now you choose r such that x r bar divided by lambda r is equal to, if lambda bar is greater than 0, lambda r is greater than 0, then you choose as the minimum most of all xi bar divided by lambda I such that lambda I is greater than 0, and you choose x r bar divided by lambda r is equal to maximum of xi bar divided by lambda I if lambda I is less than 0, if lambda r is less than 0. Fine. And if you choose this, so here you choosing r such that in this way, then we Note that X star is a feasible solution to the set S. Fine. That means X equals to B together with X greater than equal to 0. Now, here you notice that the difference between X bar and X star is that in X bar you have many column vectors, P many non-zero components. However, in X star you have P minus 1 many non-zero components. Now you consider the vectors. You consider the column vectors associated to the non-zero components of X star. The column vectors associated to the non-zero components of X star are linearly independent, then X star is a basic feasible solution to S. If the column vectors associated to, or we are just in a short, let me write it as if linearly dependent, if the column vectors associated to the non-zero components of X star is linearly dependent, then linearly dependent, then again you proceed to reduce the number of non-zero components of X star in a similar way, the way that I have followed to reduce number of non-zero components of X bar to X star. I have reduced, you notice that by the above process, I have reduced the number of non-zero components of X bar. In X bar, the number of non-zero components were P. In X star, the number of non-zero components is at least number of non-zero components are at max P minus 1. Fine. Out of these components, you may have few components 0, but here number of zeros are then n minus p plus 1, at least n minus p plus 1. So you have reduced number of non-zero components in X bar by reducing X bar to X star. And once you have reduced number of non-zero components of X bar, then you are reducing this set, that a1 a2 ap, you are dropping out few variables, few vectors here out of this, and then you are checking whether that reduced set is linearly independent. If that reduced set is linearly independent, then indeed X star is a basic feasible solution. If not linearly independent, then in that case what we have to do is again you follow the same process of reducing X bar to X star. Then in this way you are reducing number of vectors in a1 a2 a3 till ap. You are dropping out few variables, few vectors, and then at the end of the day obviously you will find that there exists a basic feasible solution to the given set capital S. So this process obviously will end up with at least one linearly independent column vectors of the matrix capital A, and that will produce a basic feasible solution. So we repeat the process. If linearly dependent, then we repeat the process. until we get a set of column vectors associated to zero components of the reduced solution becomes linearly independent. And now you may ask the following question: what is the assurance that I will be ending up with with a linearly independent set? Here you notice the following, that I was having with x bar associated columns are a1, a2, ap. Fine. And with x star, I am moving from x bar to x star. X bar, if it is linearly independent, then x bar is basic feasible solution. We don't have to do anything on reduction to x star. But if this is linearly dependent, then we are trying to drop out a few vectors from this set. And we are dropping at least the rth one, a1, a2, ap minus 1, ar minus 1, ar minus 1, r plus 1, then ap. Fine. Now you check whether it is linearly independent. If linearly independent, then fine, x star is a basic feasible solution. If this is not linearly independent, then you can still reduce it. So again you drop. So from x star you now find x double star, and then you reduced one more vector. So here you have how many? P minus 2 at max. Fine. So in this way you will end up, if you have to process in this way indefinitely means you have to reduce and reduce. Ultimately you will find that you have reduced to at least one vector, a1. Fine. And when you have reduced in this way, when you have reduced to a single vector, and this a1 is a non-zero vector, then obviously because the columns of capital A are non-zero, and therefore this a1, I'm writing here a1, instead of a1 it might be like, let's suppose ak. So in this way if you are reducing, so here in this set you have p many vectors, in this set you have p minus 1 many, in this set then p minus 2 many. In this way if you are reducing, at the end you will obviously reach at a location, at a position where you have just only one vector, and that vector indeed a linearly independent set, because any non-zero vector given, if it is given to us, a non-zero vector, a set consisting of a non-zero vector is linearly independent. Fine. So this process obviously will end up, this process of reduction will end up with giving a linearly independent set. Fine. And obviously then you are reaching at a basic feasible solution associated. So thereby you are reaching, in this way you will reach to a basic feasible solution from the given solution x bar by reducing x bar. Now let me give an example so that the idea of reduction will be clear to you. It is given that the solution x1 is equal to 2, x2 is equal to x3 is equal to 1 is a feasible solution to the set that 2x1 plus x2 plus 4x3 is equal to 1, 3x1 plus x2 plus 5x3 is equal to 14. Here it is 11, sorry. Together with x1 greater than equals to 0, x2 greater than equals to 0, x3 greater than equals to 0. It is a feasible solution given to us. Now reduce the feasible solution. Reduce this feasible solution. Sorry, to a basic feasible solution. In what way can we be able to reduce it? Now let us write the given equation in the form of x equals to b. The given system of equations is ax equals to b together with x greater than equals to 0, where the matrix A is consisting of first column, second column, third column, where A1 is 2, 3. Associated to A1 you have the variable x1, associated to A2 you have the variable x2, and associated to A3 you have the variable x3. A2 is 1, 1, A3 is 4, 5. Fine. And B is equal to 11, 14. And in x you have components x1, x2, x3. Fine. Now once the given solution is 2, 3, 1, therefore you have from the given solution x bar, which is equal to x1 bar, x2 bar, x3 bar. X1 bar is equal to 2, x2 bar is 3, x3 is 1. Fine. And we have 2a1 plus 3a2 plus a3 is equal to b. Fine. Now let us check whether these column vectors a1, a2, a3 is linearly independent. If linearly independent, then obviously it will be the solution x bar is a basic feasible solution because all the components of x bar are greater than equals to 0 and x equals to b. But here you notice that the vectors a1, a2, a3 are two-dimensional vectors. They are from R2, and therefore in a set of linearly independent vectors from R2 cannot have more than two elements. So obviously a1, a2, a3 is linearly dependent. Fine. And once linearly dependent, we have to reduce it to a linearly independent set. In what way? So here as, or without knowing that in a set of in a set of linearly independent vectors from R2, you cannot have more than two elements without knowing it. So let me check whether the set A1, A2, A3 is linearly dependent or independent. To check if the set A1, A2, A3 is linearly independent or not, we consider the equation. We consider to check whether the equation lambda 1 A1 plus lambda 2 A2 plus lambda 3 A3 is equal to 0 is having a non-zero solution. That means whether there exists at least one lambda out of lambda 1, lambda 2, lambda 3 which is non-zero, and with that lambda 1, lambda 2, lambda 3 this equation is valid. Fine. So we consider this equation, and this equation will give us the following, that you have 2 lambda 1, 3 lambda 1 as the lambda 1 A1 plus lambda 2 A2 is lambda 2 here, lambda 2 here, plus A3 is 4, 5. So here 4 lambda 3 plus 5 lambda 3 is equal to 0, is equal to 0. Now from here, let us try to find the possible values of lambda 1, lambda 2, lambda 3. Lambda 2, lambda 3. Fine. Then you will have 5 minus 4, so it is 1. Then you have 12 minus 12 minus 10, 12 minus 10, so it will be your 2. And for lambda 3 you have 2 minus 3, which is minus 1. Fine. And is equal to some constant k, say any constant k you take. So lambda 1 equal to k, lambda 2 equals to 2k, lambda 3 equals to minus k will satisfy both the equations. So for instance, let me take just, I wanted to have just a possible solution of this equation. So you can take any value of k, and accordingly you choose the values of lambda 1, lambda 2, lambda 3, and that will satisfy this equation. Letting k equal to 1 for simplicity, you can take k equal to half, k equal to 5, any value you can take. Letting k equals to 1, we see that lambda 1 is equal to 1, lambda 2 equals to 2, lambda 3 is equals to minus 1 is a solution to, let's suppose, this equation 2. Solution to 2. And therefore at least one of these lambda 1, lambda 2, lambda 3 is non-zero, and that lambda 1, lambda 2, lambda 3 is satisfying the equation 2, and therefore this set A1, A2, A3 is linearly dependent. Once linearly dependent, we have to find out what are possible values of lambda 1, lambda 2, lambda 3. Those are already found here. So therefore the set A1, A2, A3 is linearly dependent. Further, you have this equation too, that A1, I am taking lambda 1 equal to 1 to put here, then lambda 2 is 2 A2 minus lambda 3 A3. So it is minus A3 is equal to 0. Fine. And now I name it as 3. Then we have to now find the locations of xi bar divided by lambda I bar, lambda I, right? So I am now calculating x1 by lambda 1, x2 by lambda 2, x3 by lambda 3, all of them. And I will choose a particular value of r, x1 bar, x2 bar, x3 bar. x1 bar is given to be 2 and lambda 1 is 1. x2 bar is given to be 3, lambda 2 is 2. x3 bar is your 1 and lambda 3 is minus 1. Fine. Notice that you have this. Then you choose R such that xi bar divided by lambda I is the minimum most of all the positive quantities. So choose the minimum value, find minimum value of all the positive components. So here you have positive are x1 bar divided by lambda 1, x2 bar divided by lambda 2. This will give you 3 by 2 and 3 by 2 is your x2 bar divided by lambda 2. So you choose r equals to 2. By r equals to 2 means choose to drop out a2 and choose x2 bar to make 0, right? We have to drop now a2 and accordingly we have to find a reduced solution x star from the given solution x bar. Fine. Or otherwise you can choose also the maximum value of all the negative ones. That means you have x3 bar divided by lambda 3, which is indeed x3 bar divided by lambda 3. So here also you can choose r is equal to 3. Fine. If you choose r equals to 2, then in that case the reduced solution, if if we take r equals to 2, then the reduced solution x star is given by, in what way we can find x star? X star will be given by these expressions. All the components are here. This is your x star, x1 bar minus x r bar divided by lambda r lambda then lambda 1 and so on. So these are components. Let me just write x star. X star are given by, the first component is x1 bar minus xr bar divided by lambda r. So xr bar means x2 bar divided by lambda r into lambda I, lambda 1 here. As r equals to 2, so this second component will be 0. Third component will be x3 bar minus x2 bar, xr bar divided by lambda r into lambda 3. Fine. And this will now give you, now you calculate, x1 bar is given by 2 minus x2 bar divided by lambda 2, it is your 3 by 2, and lambda 1 value was 1. Fine. So 2 minus 3 by 2, then 0, then x3 is 1 minus x2 bar by lambda 2 is equal to 3 by 2 into lambda 3 is equal to 1. Fine. Minus 1, lambda 3 is minus 1, so here it will be plus. Fine. So this will be equal to half 0 3 by 2. Now you consider the vectors associated to the non-zero components of x star and check whether that is linearly independent. The column vectors of A associated to the non-zero components of x star is first component and the third component. So it will be A1, A3, and check whether it is linearly independent or not. To check if this set A1, A3 is linearly independent, we consider the equation. Let's suppose mu1 A1 mu3 A3 is equal to 0, and this is giving us mu1 A1. So mu1 A1 is the vector 2 3, so 2 mu1 3 mu1 plus mu3 into A3 is having 4 and 5 are the components, so 4 mu3 5 mu3 equals to 0. From here you will find mu1 equals to 0 equals to mu3 is the only solution, and therefore A1 A3 is linearly independent, and hence x star is a basic feasible solution to the given system. Fine. So the problem has asked you to just reduce it to a basic feasible solution. So one you have already found. However, you could have chosen r equals to 3. In that case, so for r equals to 3, let me give you the solution and you will check whether that is linearly independent. If we choose r equals to 3, then I am keeping a home task that so that x star will become the solution 350. Fine, and which is also a basic feasible solution. I'm keeping this as a home task, and I end up the lecture here. On the next lecture, we will proceed to reduce a basic feasible solution or improving a basic feasible solution to an optimum solution. So what we have done in this lecture is the following, or collectively all the last few lectures till today. What we have done is, at first we have found that the feasible solution to an LPP is a convex set, and not only convex set, it is a polyhedral set, intersection of a few half planes. Fine. And we have proven that if there exists an optimum solution of the given LPP, then that must be adjacent to at least one of the vertex. Fine. And therefore, to find the solution of an LPP, it is then very clear to us that you just find out the value of the objective function at the vertices of the feasible region, and you find out which one is the maximum most value, and that vertex will give you the optimum solution. But you notice that although for just two variable problems you have here in this figure, you have just a few vertices. A few means very few. You have five many here in this figure, in this particular figure. And but if you have a billion number of variables and million number of equations, so in that case you note that how big is NCM. Fine. If n is very big, m is also big, then in that case, for instance, you just take n equals to 10, just 10 many variables, and m is equal to, let's suppose, how many equations, 5 equations you have. Then in that case, can you just find out what is this 10c5 and how big this quantity is, and accordingly that many, at max that many basic feasible solution you may have. And corresponding to every basic feasible solution you have a vertex. So here this 10C5, which will be approximately 250 or so. So precisely it is 252, and therefore you have to calculate your objective function value at 252 points. If you have 100 and here is 50, then done. Then how large it is, and this large quantity, as there are a very large number of basic feasible solution, it is not practically possible to find out all the 52 or that NCM at maximum number of solutions to this linear equations x equals to b, and then you find out the objective function value at these all basic feasible solutions, and then you find out the optimum solution. So this is not a practically possible approach, or this is actually, this will take computational effort very high, because NCM is a very big quantity. Fine. And for each and every of 1 to 252, you have to find, a solution, you have to solve this system. Solving a system of linear equalities for a large number of variables is not an easy task, and therefore you notice that how complex is the situation when n and m are very big. And practically when you go for commodity allocation on any economics problems or any practical problems, where like a dynamics problem or scheduling problem, and or transportation problem, so there you can think how many in transportation some commodity has to be transported to different cities. And if I have, let's suppose, 1,000 cities and I have 500 commodities, then you can think how complex is the situation. And for every location path or every particular basic feasible solution, you have to solve the system of linear equations, and that will be very much tedious, and obviously by hand calculation, and not only by hand calculation, by computer also. This process will take an exponential time. We can prove that this exponential time is some kind of 2 to the power n amount of time will be taken by this process, that find the vertices, and then you find the optimum, you find the value of the objective function at the vertices, and then filter out which one is the maximum most. And in this way, solving a linear programming problem is not practically suggested or not possible either. And therefore we have to play a clever trick. Clever, what is that clever trick? Is the following: you start with any basic feasible solution, and then from that basic feasible solution, you notice that you have two adjacent vertices. For any vertex, you have two adjacent vertices if you have two-dimensional problem. And then you notice that from this vertex you calculate once this solution is given to us, we can quickly calculate this solution or this solution. For instance, here in this problem, we notice that a solution was given, and from this solution you have found two solutions, two adjacent solutions they are. And therefore corresponding to a given solution, you have not solved this x equals to b to find the adjacent two vertices. Clear? And accordingly, what is happening, accordingly, given, so once you have found one basic feasible solution, then adjacent two vertices are known to you. Now you move to that vertex which will improve your objective function value. That means if the objective function value at this point is bigger than this point, then you move to be, so you consider two adjacent vertices to move. You can move either to this vertex or you can move to this vertex. Now you calculate the objective function value at this point and at this point. If you find that at this point the function value is more than this, and at this point the function value is also more than this, then you move to this one, because that will give you maximum improvement of the objective function value. However, if you find that the objective function value at the adjacent vertices are not bigger than the objective function value at this point, then you have reached to the optimum solution. Fine. So in this way, you notice that you can, from, if this point is not an optimum solution, then you are moving to either this point or this point. So once you have moved to this point, then you don't have to calculate this and you don't have to visit this path. So you have moved to this. And at this point, now you reduce the basic feasible solution to either this or this. Now this point you have already visited, so you don't have to visit it. So you have only one point to visit. So at this point, once you have reached, then you check whether it is an optimum solution or not. And you will find that in a very less number of less amount of computation and visiting very few basic feasible solutions, you can find the optimum solution in this way, that you are at a basic feasible solution, then you move to the adjacent vertices by improving the objective function value maximum possible. Fine. So in this way we will approach in solving a linear programming problem. Just we will try to visit as less as possible basic feasible solutions, and reaching from one basic feasible solution to the, or jumping from one BFS to the another BFS, will be just a simple calculation, and that simple calculation will be known to us very shortly, and that is the simplex method. And on the next day, then we will start developing the simplex method. And before that, we require to learn a few terminologies or notations. Otherwise, the description will not be handy to us. So on the next day, we'll start describing a few notations which will be useful in the development of the simplex method. And geometrically, the simplex method says that you start from a feasible solution, then you reduce to a basic feasible solution, and from a basic feasible solution, then you move to the adjacent basic feasible solutions, and move to that adjacent vertex which gives you the maximum most improvement out of all the adjacent vertices of a given basic feasible solution. Fine. So you are in simplex method, we will just move geometrically one vertex to the another vertex, improving the objective function value maximum. Fine. This movement from one vertex to the adjacent vertices is the method simplex, and which will be known to us very shortly. With this, let me thank you. Thank you all for all of your kind attention and kind time to listen this lecture. Thank you all.